ESO telescopes are being used to search for the subtle signs of magnetic fields in other stars, and even to map out the star spots on their surfaces. This information is beginning to reveal how and why so many stars, including our own Sun, are magnetic, and what the implications might be for life on Earth and elsewhere in the universe. This is the ESO COST, cutting-edge science and life behind the scenes at ESO, the European Southern Observatory. More than 400 years ago, Galileo Galilei became one of the first astronomers to note that the Sun's surface exhibited dark imperfections, now known as sunspots. What Galileo didn't realize at the time was that these dark spots were a sign that the Sun is a magnetic star. Sunspots appear dark because in these regions, the strong magnetic field limits the transportation of heat to the surface. This process makes these locations much cooler and thus darker in appearance than the surrounding brilliant surface. As sunspots develop, the magnetic field increases in strength and complexity and becomes increasingly tangled. Eventually, for some sunspots, the magnetic field snaps and, in an instant, the energy it holds is unleashed in a brilliant and violent flash. Emerging as solar flares and solar storms, this energy is sent hurtling into space. When directed at Earth, this energy, arriving in the form of a stream of charged particles, is mostly deflected by the planet's own magnetic field. But some of the charged particles get through and create beautiful aurorae in the northern and southern polar regions. But beauty here can also signify danger. Solar storms, if powerful enough, can in turn spark geomagnetic storms on Earth, capable of destroying satellites, interfering with air traffic communication, and even crippling power grids. In a technological era, this threat is reason enough to study solar magnetism. The Sun is not unique in being magnetic. Most stars in our galaxy harbour a magnetic field of some kind. Although we don't fully understand the processes that create our own star's magnetic field, other Sun-like stars are expected to have similar properties. However, the processes that drive magnetism on some classes of distant stars, such as those that are much hotter and more massive than the Sun, may be very different. But what is known is that solar flares and storms can impact life on Earth in a profound way. Measuring a star's magnetic properties can help astronomers to evaluate how hospitable an orbiting planet might be for life. The magnetic field of a star can be measured through what is known as the Zeeman effect. Chemical elements produce narrow dark absorption lines in the spectrum of a star. When a magnetic field is present, these lines split into triples or even more complex groupings. This splitting can be measured and used by astronomers to gauge the strength of the magnetic field. But the Zeeman effect leads to an additional effect. The starlight becomes polarized. This polarized signal is the vital clue that can be used by astronomers to spot the presence of a stellar magnetic field. ESO's telescopes and instruments, such as FORS on the Very Large Telescope, are equipped to detect polarization. They are powerful tools with which to measure stellar magnetic fields. One of these instruments is HARPS, the High Accuracy Radial Velocity Planet Searcher. It's located at ESO's La Silla Observatory in Chile. HARPS very accurately measures the Doppler shift of stellar spectral lines to look for the subtle signatures of exoplanets. But HARPS can also measure the polarization of spectral lines to detect stellar magnetic fields. For some stars, this spectrograph can measure thousands of spectral lines simultaneously, helping to detect signals from even the weakest magnetic fields. By observing a certain star several times while it rotates, scientists can now use these polarization measurements to create actual maps of the magnetism-related star spots present on distant stars. Such images remain impossible to obtain directly with large telescopes, as almost all stars are simply too far away to be seen as anything more than points of light. But thanks to the huge amount of information contained in the polarized signals, we can uncover a great deal about stellar magnetic fields, revealing valuable data that would otherwise remain hidden. Astronomers have found that most stars are magnetic, but in very different ways. So different processes must be at work to generate and sustain these magnetic fields. We now know that these magnetic fields in turn have a big impact on how stars behave throughout their lives. They play an important role in the complex processes of star formation, and at the other end of stellar lives, they are vital to explaining the bizarre behavior of gamma-ray bursts, pulsars, and, most extreme of all, magnetars. Astronomers are now eagerly studying stellar magnetic fields to assess their impact on the habitability of rocky exoplanets around them. A star's magnetic field can greatly affect the amount of radiation reaching a planet's surface. Intense flares on stars produce ultraviolet radiation that is hazardous to most forms of life, both primitive and advanced. Magnetism has effects throughout the universe, from the Earth's surface right out to the most distant exploding stars. Polarization measurements help astronomers to understand the magnetic properties of our own star and all the other stars in the universe.